All right, so this is actually a new meeting. Just in case I deleted the old one and started a new one. So let's give everyone a few minutes to get back together again. But what I'd like to do first, before we dive into this exam, I just want to quickly review some of the more fundamental rules of derivatives, which we saw in chapter 12, because I think we could probably use a little bit more review of that before we get back into the sample final. So first, let me go get the slides open. Now, chapter 12, as you saw, I mean, it's really long. And so we didn't really have time to get that deeply into it. So what I thought we could do is on the actual final exam, just to have a few very simple questions about derivatives. And I mean simple, just the very basic rules that we were covering. And then the focus of the chapter can be on chapter 11, although I also want to keep a couple of questions about interest rates too, because they tie in together very well. So in other words, the vast majority of the questions will actually be on chapter 11 rather than 12, but we don't want to completely ignore 12 either. So first, let me go get 12 open here. Oh, you know what? One thing I forgot to do, I think if we had been meeting in person, our exam would have been on the 15th. Let's take a quick look at the calendar for December, I mean. Yeah, since we only meet once a week, I'm pretty sure that they would have had us do our final exam on the 15th in the class. Now, the grades aren't actually due until the following week, early in the following week. So, you know what, let's do this. I don't think you're going to need that much time, but just in the off chance that you are swamped with your other exams and all the rest, I could have you send it to me. The absolute latest that I have to have them would be Sunday the 19th, because the grades are due, I think, that Monday or that Tuesday. So why don't I make an announcement right now that if you really need the time, you can have up until the 19th, but I recommend you not wait that long if you can avoid it, because it'll start to happen is after a while, you'll start to forget what we were doing. And, let's just say maybe it's not the best move. So let me just quickly make an announcement. So this way you'll have plenty of time. And that means there'll still be opportunities to ask questions by email, or else possibly even arrange an online Zoom conference to take the place of office hours between now and then. If you want to do that, you'll, of course, send me an email and we'll make the arrangements. So let's go back into Moodle and let's make that announcement. Okay, so the final exam will be due by Sunday, December 19th at midnight. Okay. That's the absolute last time. After that, if you send in later than that, there's a very real chance that you'll end up, I'll grade it, of course, and you'll get your grade. It's just that you might get an incomplete on your transcript, or you might get no grade at all. We don't want that. Just to make sure that the grades are on time. Just, don't push it past that night. And I would obviously recommend that you send it in sooner rather than later. But you do have all that time. So if you've got other classes that you need to do first, that's fine. All right, so that takes care of that. Now, as I started to say, I think we need a little more practice with these derivatives in chapter 12. And I just want to focus on the basics because, it's a very complex topic. And then really the hope here was just to have you see what we're leading up to in Calc 1. So we're going to skip over the limits altogether. If you do take Calc 1, you can come back and revisit this material. But if not, I just want you to learn a handful of these key rules, all right, just a few. So the ones that you'll be responsible for would be basically the first, say, 7. The chain rule, we didn't have time to go over, so forget the chain rule. We'll just do these basic ones. And so, for example, we need to remind ourselves that the derivative of a constant hold on. Because yeah, these are the ones that you're going to see the most often anyway, but I just want to make sure that we understand the basics so that again, if you do find yourself in Calc 1, you'll be spending a lot of time with these concepts. But if you encounter them in another area, like in economics, for example, it's important to at least have a fundamental idea what they're all about. So first of all, the derivative of a constant is 0. So in other words, if you more formally, if you write f of x is k is some constant, that means that f prime of x is 0, guaranteed. Okay, because remember, the derivative represents a rate of change. And if this is a constant, that means that there can't be any change. So therefore, the rate of change or the derivative is 0. All right, so just think of a derivative as a rate of change. And so that's why a constant, which we know can't change, has to have a derivative of 0. Oh, you know what? Let me save this. I don't want to lose this. I'll post this as well as the solutions to the sample final, so you have everything all together. Okay. And hopefully this will help you with the final exam, of course. All right, hold on. Let me get this in here. Yeah, that'll do. All right, now the next thing we went over is this idea of a linear function. So again, remember the derivative is a rate of change, and the slope of a linear function is also a rate of change. So therefore, what that means is that if you have a linear function, the derivative is equal to the slope. All right, so let me show you a couple of examples of that. The derivative of a linear function, which is just another name for a straight line, equals the slope of the function. So in other words, I'll write out the formal definition. So it could be, let's say, mx plus b. All right, just to keep it as general as possible. The derivative would therefore just be m rather, okay? So m is the slope. And so the derivative, oh, and by the way, the slope itself is a rate of change. So therefore it stands to reason that the derivative is the slope. So for example, if I had something like this, one more thing. I just want to mention, in case it wasn't clear, we can use y and f of x to represent a function. Okay, so in other words, sometimes a function is written like this. If you have something like this, y equals 3x plus 7, it can also be expressed as f of x. It means the same thing. Okay, so in this case, f prime of x represents the derivative. And because 3 is the slope, all we have to do is note that the slope of, or derivative of this function is simply 3. Okay, so that's a very simple case. And again, it's because m is a slope already, which is a rate of change. So therefore, the derivative is that rate of change, which is the slope. Okay, so those are the two simple cases. The next one is the power of. Now, this is the tricky one. I mean, it's not that tricky, but we do need to get used to it because we're going to see it all the time. Almost every function that you'll be taking the derivative of will probably have an exponent somewhere. And so that's why this is so important. This is the so-called power rule. So just in general, for any function that's written in the following form, f prime of x would be n times k times x to the n minus 1 power. So it's really just a formula. But once you've done it a few times, I think you'll see that it's pretty straightforward. It's just that sometimes it can get a little tricky, especially when you have an implied exponent of 1 or something like that. So let me just show you a few examples. Actually, let's do this. So we'll start with this one. Now, these are very good for polynomials, but let me start with something like this, 4x to the third power. So in this case, k is 4, n is 3. K is the coefficient. And n is the exponent. So now based on this rule, f prime of x is n times k times x. Now the exponent is reduced by 1. All right, so just remember, if you apply this formula correctly, you should never make a mistake. But occasionally, you might run into strange situations. I'll show you an example of what I mean by that. Suppose you had something like this. F of x is 5x. Now, technically, this is a linear function. So you already know that the derivative here this is by the way a linear function where the slope is 5 and the intercept is 0. So you don't really have to apply the power rule here. But the point of it is that you can, because it works for linear functions as well as other types. Therefore, f of x, f prime of x is 5. But what I would like you to see is that if you apply this approach up here, and we can think of this as kx to the n power, where k is 5 and n is 1, then using our rule, the power rule that is, you'll see that you have to get the same result. Okay, nkx to the n minus 1 would therefore equal 1 times 5 times x to the 1 minus 1. And that's the tricky part right there, because this is 5x to the 0, and of course x to the 0 is just 1. So you see, I'll just mention this in passing here, but the linear function rule is a special case of the power rule. So it really isn't a separate rule at all when you come right down to it, but it's quick and easy. But just be aware that the power rule applies here also. All right, why don't we do a couple more of these? Let's try some more complicated ones. Like, for example, now what do we do in a case like this? Well, all we have to do is calculate the derivative of each term separately and then add them up. So for this term, k is 6 and n is 4. For this term, k is 3 and n is 7. So therefore, and let me just quickly remind you what the rule looks like. Therefore, we can treat each one separately. This first one would therefore be 4 times 6 times x to the 4 minus 1. And then here we would have 7 times 3 times x to the 7 minus 1. So you have 24x cubed plus 21x to the 6th. So even though there's a sum there, it doesn't really affect our results. Now, you'll see later on, and you might remember from last week, If these two terms were multiplied together, that changes everything. Or if they're divided. There's a separate rule for when the terms are multiplied, and there's a separate rule for when the terms are divided. But when they're added or subtracted, that's not a problem. We just literally calculate the derivative of each term separately and either add them or subtract them. All right, so that being the case, let me show you another one. Let's try this. How about, let's get really crazy and have one with 3 terms. Ooh, okay. Okay, so again, here k is 4, n is 5, k is, now here, k is, actually it's technically -3. So here's what we're gonna do. Let's write it like this. N is 4, and now look at this one. This is a constant. So what we can do is think of this as k equals 2, but n equals 0. I'll tell you why, because 2 equals 2x to the 0 power. And so you can actually apply the power rule even to a constant, but we already know that this is going to be 0 from the constant rule. But again, this will show us, I'll put this here in parentheses, that the constant rule is also a special case of the power rule. Okay, in other words, it's just a special edition of that, so to speak. So now we can add these together. Okay, so again, remember, if f of x equals kx to the n, f prime of x is nk to the x, x to the n minus 1. So let's say in the first case, we have 5 times 4 times x to the 5 minus 1. So here what I'm going to do is add this, but keep in mind k is negative. So it's 4 -3, x 4 minus 1. Now look at this one. Look what happens. It's going to be 0 to x. And remember, the exponent is implicitly a 0. But because we have a 0 here, all of this is just 0. 20x to the 4th minus 12x cubed. We have a 0 because 2 is a constant. But here you can see that the power rule does actually apply here, but we end up with a 0. All right, well that's, so they're all pretty much going to be very similar to each other. Anytime you have a polynomial like this, you basically are applying the power rule to each term individually and then adding up the results. Okay, now, then the two tricky ones come. We're going to have the product rule and the quotient rule. This tells us what to do if we're multiplying functions together or dividing them. Now, the power rule never stops applying, but when we have a product or a quotient, we have to do something a little differently. So let's go back to the slides for a second. And oh, by the way, this is what we were just doing. This is the reason why we're able to do what we just did. In other words, we're actually just simply taking the derivative of each term individually when we have a sum. You notice how here f prime of x is simply g prime of x plus h prime of x. So, I mean, you can think of this as a separate rule if you want to. It really isn't, but it's simply telling us that if you have a sum, then all you have to do is take the derivatives of the individual terms and add them up. The same thing is true for differences. All right, now let's go back and revisit this product rule. Now, this is where it starts to get a little trickier. Okay, so we're going to assume that we have a situation where we have two functions being multiplied by each other. All right. So if f of x equals the product of, now g of x and h of x are two other functions. They're all functions of x. Okay. So let me show you, like, for example, what if I had this? Two x plus 1 times 4x squared minus 3x. Now, in principle, you could just multiply these out and then apply the power rule to each individual term. But sometimes that's not the simplest way to go. A lot of these rules are designed to help us find the answer as quickly as possible. So why don't we try this? Let's say that this is g of x now, and this is h of x. And now each of these individually can be calculated with the rules that we've been using. So here, for example, and again, let's always remind ourselves how this power rule works, because we're going to need it on a regular basis. So for this first one, k is 2, n is 1. There's an implied exponent of 1 here. Now this 1 is a 0. I mean, sorry, it's a constant, which means its derivative is 0. But you can actually use the power rule here too, with the understanding that this is equivalent. 1 is equivalent to 1 times x to the 0 power. So g prime of x is going to be 1 times 2 times x to the 1 minus 1 plus 0 times 1 times x to the 0 minus 1. And that simplifies to 2. After all that work, g prime of x is simply 2. Now, for h of x, we have two terms, 4x squared, neither one of which is a constant. We're going to apply the power rule to each of these separately. So here we have k is 4, n is 2, k is -3, n is 1. There's an implied 1 here. So when you apply that rule, the power rule, this is our friend, the power rule, we'll use it constantly, probably more than any other rule. What do we have? 2 times 4 times x to the 2 minus 1. Oops, we're in the wrong way. 1 -3x to the 1 minus 1. So when you're done, when all the dust settles, you've got 8x minus 3. Okay, now, then we can just go ahead and make some substitutions. All right, so let me grab this. And let's just quickly remind ourselves, f of x was 2x plus 1. Oh, sorry, no, what am I saying? G of x is 2x plus 1. H of x is 4x squared minus 3x. G prime of x, we've just gotten through showing, is 2. And h prime of x is 8x minus 3. So now it's just a question of substituting them back into this equation. Now, I'm not saying it's not messy, but the hard work really is already over. Now, by the way, with these, you don't have to feel the need to simplify them as much as humanly possible. In other words, sometimes you can just leave it in a relatively complex form. We'll see how that goes here. Now, this is fine. I mean, you can now go ahead and multiply these out and combine these, but for the test, this is fine. You can just leave it like this. But yes, you can still go ahead and consolidate a little more if you really want to. You could apply FOIL here, for example. Oh, what the heck, let's do it. But just to get some practice, but I just want you to know it's not absolutely necessary in the test. You can actually leave it like this and you'd be all set. So F, of course, is this set. 16x squared. This is O minus 6x. I is 8x. And last is minus 3. So when you consolidate these, you've got 16x squared plus 2x minus 3. So that means this first part, oh, I didn't want to do that. All right, so what I'm going to do is, this is even better. I'll just split the screen. So as far as our derivative goes, the first part, f prime of x, is this piece, 16x squared plus 2x minus 3. And then over here on the right, you can see if I multiply all these terms by 2, 8x squared minus 6x, now I can just consolidate them. I've got 24x squared minus 4x minus 3. So either one is fine. All right. So just remember, now this is the rule. So what you're going to want to do is calculate g prime of x and h prime of x, and then just line them up and then plug them into this formula. And sometimes it's worth our trouble to simplify it. Sometimes it's not. It depends on what we're trying to do, but either one of these answers is fine. Now, the tricky one, in my opinion, is the quotient rule. The quotient rule is quite a mess, as a matter of fact. It's very complicated, but again, you're basically doing the same thing. You're taking whatever you have, you're splitting it up and solving for g prime of x and h prime of x, and then you're plugging them in. Okay, so let's go get that out of the slides. Yeah, look at that. Ouch, that hurts. Okay. Yeah, it'll wake up eventually. There we go. Okay, now, so let's do this as our example. All right, so this is g of x, and this is h of x. So since g of x is 3x squared plus 4x, in this first case, k is 3 and n is 2. All right, so that's as usual, that's how we approach these. This is a product rule, a power rule rather. And here k is 4, n is 1. There's an implicit 1 here. So let's see what this gives us. G prime of x will be 2 times 3 times x to the 2 minus 1, applying this formula over here. And then here we have 1 times 4 times x to the 1 minus 1. And that leaves us with 6x to the first, or just 6x plus 4. Okay, 4 because x to the 1 minus 1 is x to the 0, or just 1. Now, what about h prime of x? Now, this one's a little simpler because we have a constant involved. So if you want to use the power rule, here k is 7. Well, here you have to, with a constant, you don't really have to use the power rule because you recognize that, oops. It's just 0, but, let's do it anyway. Because remember, -4 equals -4x to the 0 power. Okay, that's why this is happening. So h prime of x, we've got 3 times 7 times x to the 2 minus 1, plus 0 minus 4 x to the 0 minus 1. But all of that goes to 0 anyway, so it's just 21x. Okay, so now let's gather up everything that we know. So g of x was 3x squared plus 4x. H of x was 7x cubed minus 4. And we just got through showing that g prime of x is 6x plus 4. And h prime of x is 21x squared. Oh, wait a minute. Oh, God, no. You know what? I just realized, no, there's a mistake here. This should have been a 3. Sorry about that. I just noticed it now. I copied it wrong. The exponent is actually n minus 1. So this should have been 21x squared. That's better. Okay. So let's fix that. Yeah, now we're good. All right, now, again, it's just a question of plugging these in to the scary formula. And so we're going to have, now, often with these quotient rules, you might be tempted to simplify them, but often it's not really worth our trouble because we can't often simplify a ratio of polynomials. Oh God, I ran out of space. Hold on a second. I'll move it down here. So for this one, I recommend you just leave it in this form, 7x cubed minus 4 times 6x plus 4 minus now g of x, which is 3x squared plus 4x. H prime of x is 21x squared. And then we can just take h of x, original h of x, and square it. So yeah, that's a tricky result. So I don't think it's worth our while to spend any time simplifying it because it's not going to change it very much. So you can leave it like that. All right, so I think we've reviewed enough of the derivatives so that when we get to those questions, you'll be in pretty good shape. The rest of them we've done many times before. So let's take a look at these. All right, so first things first. So these are our traditional fill-ins. So compound interest is interest on interest. Simple interest is interest on principal, which is the amount of money that we borrowed. Now, permutation, if you recall, this is a selection of objects where the order of selection matters. So we did a few examples of this. Let's see, maybe we can go back and find one. Just as a quick refresher, just to remind ourselves, what exactly did we do with these permutations? Okay, oh, right, when we chose the students from the class to form a club, because the order of selection determines which position will hold, the order matters a great deal. In other words, 317 means that student 3 is the president, student 1 is the vice president, 7 is the treasurer. 731, even though they're the same numbers, is a very different setup because now 7 is the president, 3 is the vice president, and 1 is the treasurer. So each selection of 3 students from a collection of 10 is a permutation. And we saw how to calculate the number of permutations by this formula. All right, we won't do that right now because we just need the definition. A combination is the case where a selection of objects where the order of selection does not matter. Okay, so we had a few cases of that. No, not the gambler, that the order matters there. Oh, where we just were asked to pick, let's say, 2 colors out of 6 for painting your house, or 2 toppings out of 5 when you go to Haagen-Dazs, things like that, where the order doesn't matter, are known as combinations, and this is the formula for combinations compared with permutations. Okay. Now, how many arrangements can be created from 6 objects? So this is simple because, first of all, an arrangement means you're taking all 6 objects and changing the order. How many different ways can you do this? That would be 6 factorial. All right, so arrangements, the number of arrangements is always n factorial. So if I have 6 objects, I can arrange them in 6 factorial different ways. So that's pretty straightforward. But remember, with an arrangement, you're not choosing objects, you're using all of them, but you're changing this order. All right, the sample space, this is a set that contains all possible outcomes of what we call a random experiment. Okay, so let's say you're flipping a coin 3 times. The sample space contains all the different ways that the coins can turn up. And so in other words, it contains all the possible outcomes. Whereas an event, this is also a set. This is a subset of the sample space. So let's say, for example, if I do flip the coin 3 times, my event might be something like this. Only 2 of the coins are heads, or something like that, because that's one of the possible outcomes. Now, the simplified addition rule, let me just quickly remind you, the addition rule, the full version of this addition rule is this. The simplified version just means you're leaving out the intersection. And you're allowed to do this, this rule, the simplified addition rule, can be used when A and B are mutually exclusive. Now, remember what that means. Mutually exclusive means that the sets have no elements in common. So this means that the probability of their intersection is 0. And that's why we can leave it out of the formula, because it's just 0. All right, now, how about multiplication rule? Now, there's a full multiplication rule and a simpler version of it. The multiplication rule can be written in 2 different ways. They're equivalent to each other. So they both mean the same thing. Now, the simplified version okay, now when are you allowed to use this much simpler rule? The simplified multiplication rule can be used when A and B are independent. And I just want to remind you too that independence implies that two conditions are true. And when they're both true, then we can use the multiplication rule. Okay, because independence means that the conditional probabilities are reduced to what we call unconditional probabilities. We don't need the conditional probabilities because they're irrelevant. Okay. And 2 requirements for events to be complements. All right, well, let's see. If their intersection is the empty set and their union is the entire sample space. Now, you can write it like this, but there's a second way of doing this. It means the same thing. Either one of these is fine because they both mean the same thing. All right, so finally, we're ready for some problems. All right, now, first of all, we're looking at some interest problems. So for this one, remember the formula we need for future values is A equals P, 1 plus R over N to the NT. A is the future value. P is the principal. That's the amount you've either borrowed or lent. R is the rate of interest. N is the compounding frequency. And T is the time. And it's measured in years. So in our case, we're putting $50,000 in the bank. Principal is $50,000, 5 years. The interest rate is 8%. And the compounding frequency is monthly. And that means that N is 12. Think of N as the number of times per year that the interest is paid to you. What else are we missing? P, R, and T. No, we got it. Okay. So we plug everything in. And now it's just a question of being careful with it. For example, 8 over 12 is actually equal to, if you divide that out, 0.00. Now here, unfortunately, there's going to be some rounding. 0.00, let's just say 6667. That's probably close enough. To the 60th power. In fact, you know what I'll do? Let's do this. Instead of writing it like this, let's just write it as 1.006667 to the 60th. And then what you should probably do on your calculator is do the exponent first, 1.006667 raised to the 60th power, and multiply that. That turns out to be roughly 1.489875. That's probably close enough. Remember, we're going to round this to dollars and cents anyway. And then we're going to get about 74,493.77. Okay. And so what that means is that you'll have that much money in your bank account at the end of the time period. You start with 50, you end up with 74,493 after 5 years. And in part B, what they're asking you to do is recalculate this with continuous compounding. And so the formula changes. With continuous compounding, we need a separate formula. A equals PE to the RT. All right, so we'll have our initial principal, E. Now remember, the rate of interest here is 8%. And it's a 5-year investment. And so think of this as A equals 50,000, E to the 0.40 power. Oh, and so we're going to evaluate E to the 0.40 power. This should be on your calculator. It's approximately 1.49, 18, yeah, we can round it, let's say 24 7. That's close enough. All right, multiply that by 50,000 and you should get within a penny, 74,591.23. Now, the important detail here is that with the monthly compounding, we had this much, but with continuous, we have this much. And so the idea here is that the more often interest is compounded, the higher should be your future value because you're earning more compound interest. But this is the limiting case. It's not possible to earn any more interest than that on this account. Okay. Now, in practice, the banks don't typically pay interest on a continuous basis, but if they did, this is how it would be calculated. All right. Nice. Now, number 2, this is a pure probability theory. Now, here we have a coin, as we mentioned earlier, being flipped 3 times. Now, the first thing we want to do in these cases is come up with a sample space. Now, this is important because if you get it wrong, you're going to get all the answers wrong. So here's a way of avoiding that. You can draw this little binary tree diagram. Each branch represents a flip. So if you start with a head, the next flip can either be a head or a tail. If you start with a tail, you can get a head or another tail. So remember, we're flipping the coin 3 times. So here, you can follow these 2 H's up with another H. Here we have H, T, H, H, T, 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 H, H, T, H, T. So I'm running out of space here, but you can see, at least I'm getting them all. Now we're going to write this out in a set. But what I'm going to do is change the sequencing slightly. Show you what I mean in a second. So what did I do? I changed the order a little bit because what I wanted to do is this. I'd like to have them organized so that I have first the number of cases where there were 3 heads. And this is just for convenience. You don't have to do this. This just makes it a little easier to keep track of what you're doing, I think. These are the 3 different cases where you have 2 heads. These are the cases, oh, no, you know what this means? I actually typed one of them twice, it looks like. Hold on a second. Yes, I did. Hold on. Jesus. I missed. No, what I did was okay, there we go. All right. So in other words, I've got this one. There we go. So they're all there. But what I wanted to do, these are the cases with 2 heads. These are all the cases with a single head. And this is the case with no heads. That's our sample space. There is nothing else that can happen but what's in here. Then we have 2 events. In case A, we have at least 1 head. So what that means is that we include everything except the case where there's no heads. Now, this is what I was saying. If you have it set up like this, look how easy this is to define our events. All I had to do is take all of them but the last one. And then for B, they're telling us B is at least 2 tails. So where would that be? All right, well, you know what? At least two tails means everything except one tail or no tail. So actually, what we could do here is three heads means no tails. Two heads means one tail. One head means two tails, and no heads means three tails. So by saying at least two tails, only interested in these two. And so it'll be easy to figure that out without missing one of them, because I'm only taking these last four cases. Oops. Okay, yeah, well, that was close. I almost wrecked the whole diagram. All right, here we go. So that means I can just grab these last four, and now I'm all set. All right. So in other words, this part is critically important, because if you don't get the sample space correct, or if you don't define the events correctly, you cannot possibly get the right answers. So with that being said, now these are easy. Now, here's the probability of A. Now, what I want you to notice here is that heads and tails are equally likely to occur. And that implies, because of the way this experiment is taking place, that so are these. In other words, these are equally likely to occur, because the probability of a head is a half, as is tails. But when you flip a second time, the same thing happens. All four of these outcomes are equally likely. And the same thing can be said for the third flip. All 8 of these are equally likely. And it's all because heads and tails are equally likely. Okay, well, what does that have to do with anything? Because that implies that the probability of A can be calculated in the following way. Since all the elements in the sample space are equally likely to occur, we can compute probability of A by simply counting the number of elements in A and dividing by the number of elements in the sample space. Which is 7 out of 8. Okay, or if you want to rewrite it as 875. Now, the other option we had was to do this. And you can see this is going to take a while, but this is an approach that works even if the outcomes are not equally likely. So this is the more general approach. But you can see this is taking a while, isn't it? And that would just be 1/8 plus 1/8 plus 1/8. And that's 7/8. So I think in this case, we might as well take advantage of the fact that they're all equally likely and just calculate it directly. But just keep in mind, this works too. Now for B, based on the same logic, since there are 4 elements in B, then the probability is simply 4 out of 8, or 1/2. Or if you want decimals, 0.5. Now with the union, what you're supposed to do is this. You should ideally identify what elements belong to that union. Now, union means you're just simply combining the 2 sets. So let's go review. Here we are. Here's the 2 sets. So if you notice, between the 2 sets, all the possibilities are covered. A contains everything except 3 T's, but B does contain the 3 T's. So that means that this union actually covers the entire sample space. And so based on that result, it must be true that this probability is 1.
15 backwards. 15 backwards. Go on.
All right, hold on 1 second. All right, now it's just 1. And also, I just want to remind you too, since A union B represents the entire sample space, the probability of S is defined to be equal to 1. So therefore, it must be 1. Now, how about this one, the intersection? This is the set that contains all the elements that they have in common. Let's see. So what we need to do is figure out what those elements are. Okay, so let's see if we can identify what they have in common. Now, again, because of the way I set up the tree, that makes this just a little bit easier in my opinion. All right, so let's see, what do they have in common? HTT, yes. THT, yes. TTH. That's it. Okay, so this set contains HTT, THT, TTH, and therefore that probability, so what we've been seeing, is very simply 3/8. Because there's 3 elements in this intersection and there are 8 elements in the sample space. Now these are easy. The complements are simple because all you have to do is this. So remember, A was 7/8, so this leaves us with 1/8 or 0.125. And B, same thing. Equals 1 minus PB, or 1 minus 4/8 equals 4/8, or 1/2, or 0.5. Now, for these conditional probabilities, here there's a definition that you need to follow. The probability of A given B is formally defined as the probability of A and B, or A intersect B, over the probability of B. The intersection we just saw has a probability of 3/8, and B has a probability of 4/8. So this simplifies to 3/4, or of course 0.75. Now for B given A, what changes is the denominator is now the probability of A. So this reduces to 3/7, and 3/7 is approximately equal to 0.429, let's say. Okay, now, are A and B mutually exclusive? Why or why not? All right, well, what does that even mean? 2 sets are mutually exclusive if they have no elements in common, since A and B have at least one element in common, they are not mutually exclusive. Now, there's two alternative ways of writing this. You can say, for example, A intersect B is not equal to the empty set. Remember, this is the empty set. If A and B were mutually exclusive, their intersection would be the empty set. Another possibility is to write this. That probability that intersection is not zero. Okay. So because they would be, it would be if they were mutually exclusive. All right, great. Now, we then have to demonstrate whether or not A and B are independent. All right, so let's get that down here. So independence, I mentioned that earlier. Independence requires two things to be true. So let me remind you what they are. So here's what we're going to do. We're going to write down the probability of A given B, which we just got through showing from up here, is 3/4. The probability of A, though, we saw earlier is 7/8. So because they're not equal to each other, that means that A and B are not independent. Okay, so in other words, because the first condition was false, we don't need to bother testing the second one. And so then we're done. Okay. Now, the third one is complements. What does it take for two events to be complements? All right, so A and B are complements if first, their intersection is empty. And secondly, their union is the entire sample space. Now, we saw before, in this case, A union B is the sample space, but their intersection is not empty. And that tells me that A and B are not complements. All right. And that's again because both conditions aren't true. One of them is, but that's not good enough. All right, now The next one involves a chart. Now the charts are pretty straightforward because a lot of the information we need is already right on there. So for example, F and D. Now, these are coffees. They're all either French roast, Guatemala, or espresso. And they're all either decaf or regular. So you can see which events are which by those letters. So F and D simply means the intersection of F and D, which is the same as saying decaf French roast. So look how easy this is. R and D is regular espresso right here. Now F is just plain French roast, okay? Regardless of whether it's decaf or regular, 0.46. R across here is the total of 0.5. Now here for these, we need the rules. For example, here D complement is 1 minus the probability of D, which you can see up here is 0.5. Then we have now here we have unions. Now, by the way, I want to mention here before we go any further that the way the table is structured, the different coffee styles, by which I mean F, G, and E, are all mutually exclusive because they can't overlap with each other. Also, regular and decaf R and D are mutually exclusive. Therefore, we can use the simplified addition rule for this problem. So therefore, what I'm going to do is go get the probabilities of F and G, which you can see are 0.46 and 0.22, and simply add them up to get 0.68. All right, now let me split the screen so we can continue to see the chart as we go along. Here we have G or E, or the union, I should say, of G and E. So here we'll just add up. G and E, so that's 0.22 plus 0.32. Okay, oh, and I forgot to mention here that okay, that's better. All right, now for these next two, these are conditional probabilities, which means we have to use the definition of a conditional probability. It's the intersection of these two events divided by the probability of this event. Now, D and F, it's right here, we saw it earlier, 0.18. That's where they overlap. F is 0.46. And so the ratio of those two values is approximately equal to 0.3913. And then we can do the same thing with the, let's see. Yeah, I want you to be able to see everything all at once. All right, here we go. So this one, so R and E is a regular espresso, that's 0.10. Oh, what happened there? All of a sudden it just moved. It's got a mind of its own. Look at that. And R and E, as I said, is regular espresso 0.10. E is the sum of column E 0.32. And that's going to give us 0.3125. All right, and then finally, we get to put our knowledge of these derivatives rules to good use. We have first derivatives, and these are the cases we saw earlier. So for this first one, since 6 is a constant, this is easy. It's just 0. So let's go back to the slides for a second. Oh, not those slides. And I just want to note here that what we're doing here is using the constant or constant function rule. It's actually technically called. All right. All right, now, this next one is a straight ahead polynomial. It's an application of the power rule. We got 3 terms, and we can apply the rule to all 3 cases. In this first case, let me write it a little bigger here. With a quick reminder that when we have f of x is kx to the n, f prime of x is nkx to the n minus 1. So here, k is 3, n is 2. K is 9, x is 1. And you can think of this one as k is 3 and x is 0. So when we apply this rule, we have f prime of x equals, okay, so this first one, remember how that works. Here it is, nkx to the n minus 1 plus, oh, sorry, you know what I did? Look at this. I wrote the wrong thing. These are not x's, these are n's. Okay, so we have 1 times 9 times x to the 1 minus 0. And then down here, we'll have 0, 3, x to the 0 minus 1. Beautiful. So the final result will be 6x plus 6x plus 9. Now, this one goes to 0. And because this is x to the 1 minus 1, this is just 9. This one is 6x. So that's our final result. 6x plus 9 is the derivative of that function. Now we have the product rule and the quotient rule. Let me go get the formulas for you. So let's treat this as g of x is 3x plus 2, h of x is x minus 4. So we'll need to calculate their derivatives and then plug them in to the product rule. This one. All right. So this, I know it's a very complicated one, but you'll have that formula right in front of you while you're doing this. So let's do these derivatives. We need g prime of x, and we need h prime of x. Okay. Now you notice it's got 2 terms. Now in both cases, there's a constant. So basically, Let's see, let me move this down here. You can think of this as having k is 3 and n is 1. Here you can think of this as k is 2 and n is 0. But we know that this one is going to prove to be 0. So g prime of x equals, so okay, so whenever we have, let me just move this. Whenever we have f of x is kx to the n, that implies that the derivative is this. So for this one, the derivative of the 3x by itself is 1 times 3, x to the 1 minus 1, 0 times 2, x to the 0 minus 1. So this one is just 3, this is just 0. So g prime of x is just 3. Well, that's nice and easy. Let me put this up here. What about h of x, h prime of x? H of x is x minus 4. Okay, so here we've got k is 1, n is 1. Here we have k is negative 4, n is 0. So h prime of x will be 1 times x to the 1 minus 1 plus negative 4, 0. Oh, sorry, it's the other way around. It's 0, negative 4. X to the 0 minus 1. This is just 1. And this is just 0. So h prime of x is just 1. That's very simple. Well, that makes things a lot nicer. So now we just have to copy, I'm going to copy these down below, and then we can just plug them into this formula. And I'm going to plug them in here. F prime of x equals g of x h prime of x plus h of x g prime of x. Now this one is nice and simple. In fact, why don't we go ahead and consolidate it? Since it's so simple. And so ultimately you wind up with six x minus 10. All right, well, that was an ordeal, but we got it done. Now, the next one is a quotient rule. So let me go grab the rule for you out of these slides. This one is a bit of a mess, but we can do it. All right, so what do we know so far? H of x, g of x rather, is the numerator. By the way, let me rewrite this a little nicer. It's 2x plus 1 divided by x squared plus 9. So g of x is the numerator. H of x is the denominator. So how do we figure out g prime of x? Well, here k is 2, n is 1. Over here, k is 1, n is 2, k is 9, n is 0. So we can do the derivatives right here. They're fairly straightforward derivatives, which makes it a lot simpler for us. G prime of x must be then 1 times 2 times x to the 1 minus 1 plus 0 times 1 times x to the 0 minus 1, which reduces to 2. Over here, h prime of x would be 2, 1, x to the 2 minus 1 plus 0, 9, x to the 0 minus 1. And that reduces very nicely to 2x. All right, so we have everything we need to come up with this formula. All right, so f prime of x, we start with h of x, g prime of x minus g of x, which was 2x plus 1, h prime of x, and all of that is divided by h of x squared, which is x squared plus 9 squared. So here, I mean, you can simplify it a little bit if you want. You don't have to go nuts. But if you leave it like this, it's fine. But yeah, we could do this. And the final result would then be okay. I don't know where this stuff is coming from. All right. All right. So anyway, yeah, we're just simplifying it a little bit. Yeah, I just realized I'm getting somehow the spacing got off. So let's see. Yeah, I gotta just clean up the mess. All right, now finally, oh, almost. So the final result, now we can just consolidate one more time. There's 2x squares minus 2x squared minus 2x plus 18. And that is the final answer. Okay. All right, so this thing is done. And so now you're officially ready for the test. I'll be posting it probably this afternoon, the real thing. And so in the meantime, remember, you can always write to me with questions. You can, if you really want to, you can arrange a Zoom session so we can go over more of these details. But I'd say that this is as far as we need to go. We're completely done. So remember, the final will just be basically mostly 11. We'll have maybe some interest rate questions in there, but and some very basic derivatives, and that should take care of it. I think that's all we can really do. We can only cram so much into this course. So I don't want to, I don't want to overdo it here. So anyway, yes, Fernando.
You said that this final will be based. You said this final will be based on chapter 11, right?
It is 11, but a tiny bit of 12. The derivatives were in 12. The interest rate questions I think, were in 4. So we'll just have some interest rate questions, all of 11, and then just the very basic derivatives formulas for 12. Because if you looked at 12, you saw that it had a lot of material in there, and we're only going to be able to use just this little sliver of it. Don't worry don't worry about the more advanced drill. Just what we did here. Okay?
Yes, thank you.
All right. And also, I'll have the exams corrected. Your second midterms, I'm still working on. They'll probably be ready by the weekend. I'll post all the scores in Moodle, so you'll see how you did. And then if you want, I can show you, go over it with you, how you did. Yeah, Fernando?
I'm sorry, I got one last quick question. I was emailed recently about a survey to do about your class.
Right.
And giving this survey from other classes as well. And I wanted to ask, when I was looking through it, I wanted to ask, what is this academic unit, like this class? Because it doesn't say what specific in the survey, like, mathematics and all that stuff. Like, that's what I wanted to know, because
I can't imagine what else you would put there but math. Academic unit, it's kind of a clumsy way of saying what department is this coming from, I guess. I assume they mean math.
Yeah, I mean, because there's other ones that are saying like humanities, liberal arts, and other ones, and then
I just put math. It's fine. Yeah, I don't know how else you would classify this as math, but ultimately, now as long as they know who this is meant for, like this class, it almost doesn't matter. But I would recommend that you write down the word math.
Okay. All right.
Yeah, some schools would say, well, that's part of the arts and sciences and all this and that. Just put math. They'll know what it is.
Yeah. All right. Thank you.
All right. All right. So are there any last minute questions? If not, you can go home. Well, you are home. We can stop early today because we're completely done with all the material. And then, like I said, you've got about 10 or 11 days to get your final exam done. But, you can also still continue to send me questions if you have any. And like I said, I'll be trying to wrap up those second midterm scores by the end of the week, and then we'll be all set. Okay. Now, I know this was a very bizarre semester because doing math online can be very challenging, but we got through it, didn't we? And so in the future, I believe their intention is to have only in-person classes from now on. So I think this is the end of the line for the online stuff, but you never know. But I'm pretty sure that that's their plan, that from now on it's just in person. And, there's something to be said for doing this in person. Obviously you have to go to the class and everything, but I personally prefer to do it in person, but, we did what we had to do. And I think hopefully everything worked out well. And you can keep all those notes, you might as well hang on to them. You might need them one day. And by the way, if you lose them, you can always write to me and I'll send you another copy. Sometimes I get emails from people from past semesters and they'll say, oh my God, I lost all those notes, but the Moodle is no longer available to me. That's okay. I have everything right here. And, like I said, because it's very possible that some of you might go on and take more math classes. And if you do, then all of this will be very, very important. If not, well, you've got more math than most people in your background, and that's only going to help you. All right. So I guess we're done. And so I guess you never know. I might see you again. I think I mentioned, just in case you are interested, we're running a statistics class during the winter session online. And if you need more math credits, it's something you should consider because statistics is really meant to be very, very useful and practical. You see it in a lot of disciplines. So if you need a practical math course or elective or whatever, it's on the table. It's, if you go look, you'll see that it's in the schedule. You may not want to spend your Christmas break doing, statistics, but on the other hand, you'll be getting those credits out of the way, and that could make your future schedule a little bit smoother. So at least it's something to think about. And for sure, you'll be able to handle it. It'll actually be, in my opinion, easier than this class. So in fact, we've already covered a little bit of the content from there anyway. So anyway, so if there's nothing else, I guess I'll just hope you all have a very nice Christmas break. And by the way, here's another interesting thing that's happened to me already. Since we're online, it's hard for me to see you, and I may not even know what you look like. If you see me in the spring walking around, you can feel free to come up to me and say, hey, how's it going? I was in your pre-calculus class, because I probably won't recognize you. That's fine. Now, I like that anyway. It's fun to meet up with people after the class is over, but it's very possible that will happen because it's already happened to me. And somebody came up and said, hey, you remember me from so-and-so class? And I had to admit that I didn't, because it was an online class. But so hopefully all this weirdness will be over very soon, and everything will be 100% normal in the spring. Okay. All right. Well, anyway, I guess we're done. So I'll see you all maybe one of these days in another class. If not, good luck. Oh, you're welcome. I thank you. I hope I need a break. Let me tell you, this has been a very bizarre semester for me, because at some of my other schools, the classes were back in person. So I'm sort of rotating back and forth between online and in person, and it's been very strange. Okay, so, all right, thank you.
Thank you,
Bye,
Professor.
everyone. Thank you.
You have a nice break too.
Oh, thank you. You too.
All right, I'll keep in touch with you if anything.
All right, good.
All right, take care.
All right.